Digital Education Initiative of Dr. APJ Abdul Kalam Technical University. Here is another lecture from subject VLSI technology having subject code KEC 053, and I am your faculty Sangeeta Mangesh from Electronics and Communication Engineering Department, JSS Academy of Technical Education, Noida. The topic for the lecture is oxidation, part 2. In the first lecture on oxidation, we have studied the growth kinetics and we have studied the different functionalities served by the oxide layer, and that is the very much cause, or that is what is the reason behind selecting silicon as the most preferred material in the integrated circuit industry. In today's lecture, we are going to study, or what are the contents of this lecture are basically you are having oxide techniques or the equipments which are generally used for oxide growth. Then we are going to study what is the difference between dry and wet oxidation, which are the two common methods of oxide growth. At the end of this lecture, as a student, I expect you to understand and explain the silicon dioxide growth process and the equipment which is being used for this particular technique, the features of those equipments, and secondly, I want you to compare or to understand the difference between the wet and dry oxidation process as far as the feature of oxide growth is concerned, on aspects of rate of oxide growth and other aspects of the layer which is being formed. On those parameters, you should be able to compare the two oxide growing techniques, that is dry and wet oxidation technique. Now, first you know already when oxide, you have silicon dioxide process, we have seen that 0.44 D of silicon is consumed whenever 1 unit or 1 D of silicon dioxide is formed. So, it first penetrates into it and then grows. So, you have very good adhesivity, very good what you call surface adhesion. Contamination is minimum because all the species are contaminant species are remaining outside, since the growth is inside, or the growth is growth is happening inside the silicon surface. So, your interface is basically initially the surface was here and now initial silicon surface was here, this was the initial silicon surface, and now the silicon surface has gone inside, here you are already having SiO2 layer. Now, this is what is the beauty of it, and that is why we have popular oxide, that is silicon dioxide is the most popular silicon oxide layer which is grown on silicon, making silicon as the preferred material. Now, since the one of the most recommended process is the thermal oxidation, and this thermal oxidation is carried out in the atmospheric pressure and temperature between 800 to 1200 degrees centigrade. You know, silicon is temperature melting point is above 1400, around 1400 plus. So, naturally at this temperature you will won't have any harm to the silicon substrate. So, deposition will be properly done. The appropriate gases like oxidizing species are made to flow onto the surface, and the oxide growth is basically initially what we do is we allow the purging of nitrogen or some other species, so that the cleaning of the wafer takes place, and then subsequently the oxidizing species are made to flow over the wafers and the oxidation process is carried out. There are two reactions which are happening. Wet oxidation is taking place in in presence of moisture, that is H2O, giving H2O and hydrogen, and second, that is dry oxidation is happening in the presence of oxidizing species, that is oxygen, giving you silicon dioxide. Here please note the safety concern related to hydrogen. So, naturally moisture like wet oxidation will have this particular concern to be taken into consideration, because hydrogen when you want to release it has got explosive nature and you need to take lot of safety measures while handling such equipment. Now, let us go ahead with what are the equipments which are being used. That is just a note of caution, whenever you consider such reaction you should keep that thing in mind. That is why I am just giving you that cautionary note. Now, here and that you must remember basically. Now, here this is the furnace which is being used, it is a horizontal furnace similar to our epitaxial growth process. But here please understand, the oxidizing species are landing up or arising the on parallel to the, okay, not parallel, but perpendicular, normal to the wafer surface. Now, here you are having, okay. Now, normally you do not recommend the resistive, okay, resistive heating, rather than that you go for RF heating. The advantage of RF heating is your furnace wall will remain cold, and therefore, there will be minimum deposition on the furnace wall, and thereby minimizing the contamination, or that is what is the purpose, that is how it will improve the yield. Now, any yield or any efficiency of the process will be number of oxidizing species which you have used and the number of oxidizing species that have resulted into the growth of oxide layer. If the species are not being fully used, you are wasting the gas which is, or wasting the species which are like source which is being entering into, like which is allowed to enter into the furnace. So, you do not want that to happen, you want entire species which are like oxidizing species which are entering should result into the oxide growth, and for that very purpose you ensure that there is proper temperature being maintained, the wafers are maintained at, okay, normal temperature, like moderate temperature, so that we will have these silicon wafers will have exact deposition happening, and there is no deposition onto the wall of the furnace. Now, this particular, okay, and this it is controlled with plus minus 1 degree, entire process, or like this entire chamber temperature is controlled, and you will have thin oxide layer growth. Initial is linear rate, and that is how it will keep on increasing, okay, increasing linearly. Always one important thing to be remembered is, unless and until you carry out pre-oxidation cleaning, you are not supposed to go for oxidation. Any process, we have already seen different cleaning techniques. So, cleaning is an essential component before initiating any of the process in case of VLSI. Cleaning is mandatory, and similarly here also, before progressing the oxidation process, you carry out normally in situ cleaning by thoroughly clean. Initially the wafers are thoroughly cleaned and all the traces of metallic impurities and organic materials are removed. The typical process of cleaning is RCA cleaning, where you are having ammonium hydroxide and nitric acid and ammonium hydroxide, hydrofluoric bath, and hydrochloric acid and hydrogen peroxide being used in as for the cleaning. So, this is basically a 3-step process, and every step RCA cleaning, you have 3 stages: NH4OH, H2O2, HCl, H2O2. This is first step of cleaning. Then water rinsing, that is DI water rinsing, then second stage of cleaning, then again DI water rinsing. In between you have HF bath to H away whatever native oxide layer is being done, and similarly after the cleaning, intermittent cleaning with DI water, thoroughly rinsing with water, we carry out spinning also, so that there is no moisture content present onto the wafer surface. After that, again second second measure for carrying out the further cleanliness, we purge nitrogen prior to and post oxidation. Now, this is very important, because nitrogen acts as a it controls, basically it controls the rate at which the oxidation has happened, and it basically drives away, like it is very good controlling agent in case of my process of oxidation. Now, I told you there are 2 ways in which this oxidation process is happening. One is dry, another is wet. So, we are going to study first what are the thermal oxidation processes which incorporate dry oxidation. Now, here the oxide is basically grown, and if the thickness of oxide is less than 1000 angstrom. Now, if my thickness of oxide is less than 1000 angstrom, then only I will go for dry oxidation. It is a slow process, and the rate at which the oxide grows is approximately 140 to 250 angstrom per hour. this is what is the growth rate. It is very suitable for thin oxide growth, thin oxide layers which are to be grown. You can activate or you can increase the growth rate. We are also going to see in the next lecture whatever are the influencing parameters that hamper or that enhance the growth process of the oxide. So, we will highlight those things also, but just keep in mind that you can control or you can enhance the growth rate if you use some halogen species or you use some if you have additional chemical species which are to oxygen decrease the oxide growth. In certain cases we can have, if you have hydrochloric acid, you have trichloroethylene or trichloroethane, these things will hamper the growth rate and reduce the oxide. So, decreasing pressure also slows down the oxide rate. The oxide growth is basically dependent on different species. You have pre-cleaning also plays important role, then we are going to see that in detail, but let us highlight over here also. Whenever you are growing the dry thermal oxidation by dry process or dry oxidation is happening, you have several parameters which can further slow down the rate at which the oxide growth is happening. Now, this oxide rate can be reduced and pressure also plays important role, decreasing pressure also reduces the oxide rate. Now, there are plus and minus points related to the oxide rate also, rate of growth also. We will see them in the subsequently. So, let us remember these points first and then we will go. So, these are the chambers where the oxidation is happening. Here you will see the vertical stack, here you are having these here you are having this is the wafer stack where your wafers are placed in this manner. Here you are having this is the stack where your wafers are being placed. So, you have this is the vertical tube furnace where wafers are being loaded slowly one by one. From here you will first load and they will get substantially loaded over here, and here you are having this is the loader where you are loading the wafers. So, you have two types of furnaces, vertical as well as horizontal, where your wafers can be loaded and the oxidation, this is the entire equipment which is being used for oxidation. You have a panel where you can set all these parameters and subsequently load your wafers and carry out the operation. Another so this was about the oxidation. Now, when you go for wet oxidation, a popular method is known as bubbler, where you are having a glass flask, and this glass flask we refer as bubbler, and it contains deionized water and it is attached to the oxidation tube. You boil this water, or prior to boil point basically you bring it to 99 degree centigrade, 100 degree pe prior to that. So, like 100 degree pe water normally boils. So, you convert the water into vapors, and those vapors are allowed to flow or allowed to they are made to flow over the wafer substrate, and that is how the carrier gas will be nitrogen, which will allow those wafers to or those water vapors to flow over this particular substrate and thereby producing the oxide growth. Now, this vapor it becomes saturated with water and the vapor travels into the oxidation tube, where the additional heating will also happen, and slowly this is the tube, this is the tube through which the vapor will be flowing, and you will be, this is basically a low simple demonstration kind of thing. It is not being commercially being used, but this is the process, general process which is being incorporated. The oxide rate is hard to maintain with the bubbler method, because the difficulties involved in the controlling both the amount of water vapor entering into the oxidation tube and the temperature of the water, as well as the risk of contamination during the transportation. So, we have another method where we are combining both oxygen and hydrogen, and they are made to combine over here within the chamber or within the tube and then made to. So, this is basically a system where instead of boiling water and moisture, this water vapor getting made to flow onto this particular substrate, what we do is we combine and then here we produce the moisture. So, you do not have any contamination happening. So, this is happening within the chamber itself, and you have your wafers kept over here. So, naturally from one end you have oxygen another end you are having hydrogen, both will be allowed to combine with each other to form water vapor, and you will be allowed to have the wet oxidation process, where SiO2 okay, Si will react with 2 molecules of water and form SiO2 plus twice H2. Now, what I told, this particular cautionary word comes over here. You have hydrogen getting produced as a byproduct, and which is to be handled very cautiously, because it has got explosive nature, which is that is why there is a lot of safety concern involved while handling such systems, that is wet oxidation process using combination of hydrogen and oxygen like this. Then you have another method or improvisation, where you are having H2O being inserted and carrier gas is inserted from another chamber, and you have your hot plate on which you are So, you have basically the problem of controlling the gas flow. Here you are having this particular moisture, this is basically water vapors, you are having water vapors. These water vapors are made to pass through this flash valve. Now, this flash valve is basically giving you additional controllability, what was lacking in my bubbler. And here, since it is combining over here, there is minimum possibility of contamination, and then subsequently you have ability to flow or make this particular gas enter into the chamber and oxidation to happen or silicon dioxide growth to happen, so that contamination free controlled growth can take place onto the wafer substrate, and proper oriented, whatever orientation of the this thing will be, amorphous silicon will grow onto it. So, this is what is known as, this is the most popular method, where you are having controlled as well as no contamination or contamination free oxide growth. So, let us now compare what exactly are the two processes. I told you already, when oxidizing atmosphere contains water vapor, the temperature is between 900 to 1000 degrees centigrade, I call it as a wet. Here, when oxidizing atmosphere contains oxygen and the temperature is little bit higher, then I call it as dry oxidation. Now, please understand, here when wet oxidation is happening, the growth rate is normally moderate to high as compared to your dry oxidation, and thereby imagine a situation where molecules of oxidizing species are coming hurriedly and trying to position themselves onto the growth onto the substrate. Naturally, there is more possibility of deformities or surface or trapped impurities between the layer, or defects getting accumulated onto the surface, and that tendency is too much in this particular case or wet oxidation. The rate of oxide growth is much higher as compared to dry oxidation. It has got vapor water, then you have byproduct of hydrogen which is being used, and that hydrogen has to be handled very cautiously because it has got explosive nature. Whereas, and the reaction is, many times we have done this, Si plus twice H2O, 2 molecules of water will react with one single molecule of silicon to form SiO2 and hydrogen. This hydrogen is basically a safety concern related to it. The application of this is, since the oxide growth is very high, you have thick oxide layer being formed. Wherever you need field oxides, you go for these kind of oxide layers, that is wet oxidation. Whereas, so that means quality of the oxide layer will also be compromised to some extent in case of wet oxidation, because the rate of oxide growth is much higher as compared to your dry oxidation. Now, imagine a situation where the oxidizing species are rapidly penetrating and accumulating, and that is thereby forming the oxide layer. Since the mobility is much higher, the rate of growth is much higher, there is every possibility the quality of the oxide layer getting compromised, or it will have some impurities getting trapped, some defects getting trapped, and that is why your quality of the oxide layer will get compromised, whereas in this case the growth process is happening, though at elevated temperature you will have very good oxide growth happening. The reaction is Si plus O2 forming SiO2, and the application of this particular thing includes the normal thin films wherever you want some what you call, or in scale devices also, if you need thin oxide layer for insulation, or you need this oxide layer for preventing passive like active area covering or preventing the passivation of the surface, that has to happen. Or if you want selective what you call oxidation for prior to like as a protecting layer for covering the underneath surface, for those purposes if you need a thin layer of less than 1 nanometer. Okay, this should be okay. This is basically we have seen already. Here the growth rate is around, in case of wet oxidation the growth rate is in thousands of angstrom per hour, whereas in case of dry oxidation the growth rate is around 150 to maximum 300 angstrom maximum, whereas here you will have around like it will be in the range of 1000 angstrom only. So, here I mean to say, and here I mean to say, this is with respect to dry oxidation, this is with respect to wet oxidation. So, we have compared both the oxidation processes, and accordingly we will be applying them or using them in different applications. So, we have seen this particular method. Now, there are some advanced techniques also which are being used. Now, what are those advanced techniques which are being used? So, please understand, both these techniques are predominantly being used, and depending upon the applications, depending upon the quality of the oxide film which is required, we will be going ahead with the particular processes. If I require very thin film and I don't want to compromise with the quality of the film, then I will go for dry oxidation. If I can compromise, I want thicker layer, quicker layer, and I don't want to like, it's not that I can't get good quality, I can get good quality with wet oxidation also, but I need to use a proper mechanism for controlling the moisture or vapors also which are flowing. So, controlled, you need lot of precautions to be taken. So, under those situation you can have this particular wet oxidation, but remember wet oxidation rate will be always higher. You can enhance in case of dry oxidation also, you can have halogen species or control pressure and all those things. You can have other parameters, controlling parameters, make use of those. Now, again if you are using additional measures, that will enhance the cost of the process. So, please remember, depending upon the application, depending upon the characteristics of the films which are desired, we will go for selection of wet or dry oxidation. Both are equally popular in case of IC what you call fabrication, both are being used predominantly. There are some additional methods also. One of the method is anodic plasma oxidation. Now, what has happened? It has all advantages associated with the high pressure technique, and it also offers the possibility of growing high quality oxide layers even at low temperatures. Now, there is a tendency, whenever the temperature is elevated, these defects get penetrated further down the surface, and you do not want that to happen. And therefore, since you know already silicon is a brittle material, you need to handle it very cautiously, and you do not want any impurities to get further get penetrated inside the wafer substrate. So, for that reason you are supposed not to increase the temperature of the surface of the wafer, or wafer is not supposed to be heated, and therefore, for oxidation, during oxidation, if you want the process to be what you call carried out at lower temperatures, we can carry out such pressure high quality oxide layer using plasma. Now, what is being done? In this case, you will have a low pressure process usually carried out in case of you will have discharge of oxygen. You will have plasma is basically sustained either by high frequency or DC discharge and placing the wafer in the uniform density region of the plasma. So, what do? We create the plasma, place the wafer where there is uniform density of the plasma, and then these oxidized oxygen charged species will be penetrating into the oxide layer and form the silicon dioxide. This rate is typically higher if you have surface temperature is slightly more. The plasma density and substrate dopant concentrations also play important role in this plasma oxidation. Another is rapid thermal oxidation. Here also you will elevate the temperature, the equipment is slightly what you call complex. The radiation source as well as the temperature monitoring is also an essential parameter to be taken into consideration. Both thermally activated processes and non-thermally activated processes are being used. Over here you have non-thermally activated called photon induced process, where you are using monatomic what you call oxygen atoms which are made to flow generated by UV radiations and creating them parallel oxidation reaction in the dominant lower predominantly low temperature mein you will create UV radiation, say you will energize these oxidizing species and made to flow onto this particular surface and you will create. Now, activation energies differing from those measurable are conventionally they are basically conventionally grown oxides. The activation energies will differ in this case. In initial stages the order will be 20 seconds. RTO growth rate will be linearly followed by non-linear, as Deal and Groove method has told us. Initially it will be linear rate, B by A rate constant, after that it will be under root B B into T plus tau. So, this is how the region is hardware dependent and particularly the heating source which is being used. So, you have different techniques what we have studied. So, we have studied wet and dry oxidation techniques, then specialized techniques which include plasma oxidation, where we create plasma and by DC or RF heating you create the plasma. Those oxidizing species are made to flow over the surface of the silicon and they will react, and controlled environment will be presented by controlling pressure and temperature, and then the oxidation will happen at a lower temperature. Another method we have seen where we have thermally grown, like rapid thermal oxidation we have seen, and this is how we have different methods of oxidation we have summarized in this lecture. So, if you are at the end of this particular thing, if you are able to answer or if you are able to describe at least one technique of dry and wet oxidation, if you can suggest oxidation technique along with justification for a particular MOS device, if you want to go for thin high quality dielectric layer to be grown, what kind of method you will use, whether you will use dry or wet. Here, since you want high quality thin oxide layer, we will go for dry oxidation. Expected growth is more than 1000 angstrom per hour and you need thick film oxide, we will go for wet oxidation. So, if you are able to find out these, describe the features of high pressure, plasma and rapid thermal oxidation. Important features we know already, what all the plasma may we are controlling plasma, rapid thermal may we are controlling temperature and other species which are being controlled, DC sputtering, other things are being controlled, and that is how we are controlling the oxide growth. So, if these things are clear, we will further go ahead with different aspects of oxide growth and the oxide layers in the next lecture. So, thank you, God bless and good luck.